We are looking at applications of quantum field theory to interacting quantum many-body systems. For simplicity, we focus on bosons, which are described by scalar fields, and which is non-Hermitian because if our bosons are atoms, for instance, an atom and an anti-atom is not the same thing. We started with a Lagrangian for a relativistic system with a phi-4 term, describing a contact interaction between the particles. If this is the only term which describes interaction, we have to take lambda greater than 0 in order to have a ground state. We then took the non-relativistic limit and obtained a Schrödinger-like Lagrangian with, again, in contact interaction term with a phi-4 dependence of the field. The relationship between the non-relativistic coupling constant G and the relativistic one showed us that for lambda greater than 0, we need to have a repulsion that is G also greater than 0. We then went through the process of canonical quantization. We expanded our field operator in a box, and we got our Hamiltonian, which is a sum of a one-body kinetic energy and a two-body interaction part. This two-body interaction is usually too complicated to solve exactly, and therefore we introduce the mean field approximation, leading to a set of Schrödinger-like nonlinear equations for each single particle, evolving in a self-consistent mean field which depends on the density and which is created by the ensemble of all the other particles. Mean field equations are of course not exact and often require to do some work beyond the mean field approximation. This can be done, for instance, starting from the many-body perturbation theory and adding more diagrams, or using other techniques which at the lowest level of approximation always end up to the mean field equations. An example of phenomenon which we can't describe with such simple mean field approximation is the superfluidity in cold bosons. There are different techniques in order to describe this superfluidity, for instance, the Bogoliubov transformation. But that's not the approach we are going to take. In fact, we are going to show that we can describe some phenomenology of superfluidity using some of the quantum field theory tools we have introduced earlier, in particular with the Goldstone mode. But before we get there, we need to introduce a chemical potential to our Lagrangian. This is required to constrain the number of particles in the system. Indeed, in standard quantum mechanics, we don't need such chemical potential because simply we describe our system in a Hilbert space with a fixed number of particles, and all the operators act on this Hilbert space. However, in quantum field theory, we live not in a Hilbert space, but in a Fock space. A Fock space is the sum of all the Hilbert space for all the numbers of particles. So it's a sum of the Hilbert space for one particle, for two particles, for three particles, etc. Indeed, we see that nothing in the Lagrangian specifies the actual number of particles, and we have these operators A dagger, which create particle, and A, which annihilate particle, and which can take us from one Hilbert space to the other. We also see that if we look for the ground state of the Hamiltonian, in particular in the case of a repulsion, so when G is positive, we will find that the ground state is obtained for no particle at all. And if we want to fix the number of particles, if we want to describe a system with a given number of particles, we need to modify the Hamiltonian and therefore the Lagrangian in order to constrain the number of particles, and we need to do that with a chemical potential. The addition of this chemical potential to the non-relativistic Lagrangian constrains the average density and therefore the number of particles in the system. Indeed, we should recall that the Lagrangian is a kinetic energy minus the potential energy, so therefore this is a negative potential energy. So we gain energy by adding particles, by adding a density in x, because phi dagger phi are expressed in the position x in space-time, and phi dagger x phi of x counts the number of particles in x. So we gain energy by adding particles in x with a chemical potential, and this process stops when it is counterbalanced by the repulsion between the particles. The chemical potential therefore needs to be proportional to the coupling constant G, because the more the repulsion, the harder it is to add new particles, and therefore the stronger the chemical potential needs to be. And of course, for G equals 0, where the ground state can be found to have a finite number of particles not moving at all, according to the kinetic energy, and therefore, in this case, we don't need a chemical potential. So the chemical potential ensures that we have a finite number of particles in our system.